Newton's laws of motion are some of the laws that are tackled very early on in one's physics education. Many times, this leads us to being able to state them, but not to really understand what is going on. In this video, I'll go through them in a little bit more depth, which will hopefully give you a better understanding of this important step in modern physics. In his work about motion, Isaac Newton came up with 3 laws, which we refer to them as being of motion. However, calling them as such can be a bit misleading. It is only the first 2 laws that deal with forces and the motion of bodies. The third law, however, only deals with the way the bodies interact with each other as forces are applied. It does not deal with motion. For the purpose of this video, I'm going to start discussing the third law first, and then move on to discuss the other 2. The third law states that for every action there is an equal and opposite reaction, which simply means that whenever we exert a force on a body, we expect a force that is equal in size pushing us back. The action is referring to the force that is being exerted on the body, and the reaction is the force that the body exerts on whatever is performing the action. If the person decides to push even harder, then the wall simply reacts to this increase in force by offering an even greater reaction. It is important to keep on thinking about forces here and try to avoid thinking about motion at this point, because this law just deals with forces. Let's just focus a bit on what is going on at the point of contact and why there will always be a reaction to the action, and they will always be equal in size irrespective of any state of motion. We need to remember that all matter is made up of atoms, and for the person to exert a force on the wall, he needs primarily bring in his atoms from within his hand in close proximity to the atoms making up the wall. When the person uses his body or muscles to exert a force, he is simply forcing his atoms closer to those of the wall. But why are there opposing forces here? To understand this, we need to take a closer look at what the atoms in our image represent. The nucleus of the atom is made up of neutrons, which are neutral, and protons, which are positively charged, making the center of the atom carry a resultant positive charge. Surrounding the nucleus are much smaller electrons that carry a negative charge. This means that the outermost part of an atom is essentially negatively charged. So bringing in 2 atoms next to one another is going to bring 2 negatively charged regions close to one another. And we know that like charges repel one another. So why is there always a reaction to the action? Negatively charged region 1 repels negatively charged region 2 away from it, whilst region 2, also negatively charged, is repelling region 1 away from it. This is why the pair of forces on 2 bodies will always be equal and opposite, because at the end of the day, the outermost part of both a person's hand and the wall are simply 2 negatively charged regions. And this is the case whether the object is stationary, moving with constant velocity, or even accelerating. The state of motion does not matter. Having tackled the third law, I would like to turn our attention to the first law, and this states that the body at rest will remain at rest whilst the moving body will keep on moving at constant velocity, provided that no resultant force acts on that body. Let us first discuss what is being said here. So as we've been discussing in Newton's third law, if a person exerts a force on an object, we can expect the object to exert a force that is equal in size and opposite in direction. The focus of the first law, however, is simply on the object and the forces that the object is experiencing. The person is a completely separate body from the object, and any force that the person experiences acts exclusively on him. So we can completely disregard the forces experienced by the person, as the first law does not consider the forces on other bodies, even if they are the result of a reaction. There are, however, other forces that may be experienced by the object. Friction is one of these forces that is exerted by the ground on the object. A resistance is another force that can be considered if the object will be moving through air, and it is a force that is experienced on the frontal surface of the object. Many times, to simplify calculations, air resistance is taken as being negligible, and I will do so as well, so as to be able to develop the discussion in a simple manner. So having analyzed what forces are acting on the object, we can turn our attention to the motion of the body. With the first law, Newton is stating that if the net amount of force is zero, the object can be in one of two possible states. It can either be stationary, and if so, it will keep on at rest until there is an imbalance in forces, or if it is moving, it will definitely be moving at constant velocity. Not so difficult, right? So, why do many students carry misunderstandings with this law? The main issue lies with confusion between the third law and the first. Whilst for an object such as our white box here to experience a force, there needs to be an action, this will always result in a reaction back. The key thing to realize is that these are two completely separate objects, and that Newton's first law only discusses one object at a time. Just to cement this further, we could apply the first law to the person exerting the force on the object as well. Newton's first law would still work, provided it is applied to just one object. We are again to try and analyze all the forces acting on the person, and apart from the reaction, there is also some frictional force that the ground is exerting on the soles of his shoes. If the person starts at rest though, and the sum of forces equals the force exerted by the person on the object, then the person will not slide backwards whilst pushing. Therefore, in such a scenario, we can apply Newton's first law to either the person or to the object, and in an exam situation we apply it to the person or to the object separately based on what is asked. Moving on to the second law, it states that the acceleration of a body in a particular direction is proportional to the resultant force acting on that body, and this law is quite possibly the easiest one to digest. With a net resultant force acting on the body, there is only one state of motion that the object can be in, and that is that of accelerating in the direction of the resultant force. So to conclude, let us consider a more advanced scenario where we can deal with all three laws of motion at once. Let's assume that a golf ball is thrown towards a thin sheet of metal with enough force to be able to dent the sheet at the point of contact. We can divide this motion in three separate events. The first part of the motion consists of an acceleration. This is because the golf ball is experiencing a force as it is thrown. This force will stop acting on the ball as soon as the ball leaves the person's hand. The second part of motion consists of a period where there is no resultant force acting on the golf ball. This means that the first law can be applied here, and since the golf ball was already moving, it will keep on moving at constant velocity. Which brings us to the last bit of movement, where the golf ball starts hitting the metal sheet. And this is a tricky one. The golf ball now starts exerting a force on the metal sheet. We can call this the action. The metal sheet in turn reacts to this by exerting an equal and opposite reaction on the golf ball due to electrostatic repulsion, as we've seen earlier in the third law. However, it does not stop there. The reaction is a resultant force on the golf ball. From Newton's second law, we know that this will decelerate the golf ball as it starts hitting the metal sheet. On the other hand, the action also acts as a resultant force on the metal sheet, causing the metal sheet to accelerate as per Newton's second law as well. As the golf ball decelerates, it is transferring some of its kinetic energy to the metal sheet, whilst the metal sheet is gaining energy in the form of kinetic, which will mainly be eventually dissipated as heat. The golf ball will keep on denting the sheet until it loses all its energy, which is where it comes to a halt. And if we are to be pedantic, Newton's first law can again be applied.